Hello, this is Joel Schultes of University of Colorado Boulder, Colorado Mesa University, and I'm going to give an update on some of the hydrologic monitoring data analysis we've been doing from the data we collected in 2021. Thank you to the partners. I won't take the time to go through them all here, but many people came together to provide help and funding and support to install this equipment and make this project happen. Quickly on the premise, impacts to streams, which can include direct or indirect impacts, can lead to incision and simplification of stream systems, of wetland systems, and this reduces their ability to store water, sediment, and carbon. On the top right, we see a stream, kind of quote unquote disturbance. Of course, in the Badger Creek area, maybe there wasn't even a channel, just a flat valley bottom with wetlands and no channelized flow. But due to various impacts, direct and indirect, channelization and incision can happen. This lowers the water table and allows floods to pass through more quickly, eroding more sediment and retaining less water in a particular reach. This, of course, reduces habitat quality and quantity and can reduce the quote resilience of our streams to floods, droughts, and increasing temperatures. So we're looking at restoring storage and connectivity in stream corridors and wetland corridors, and looking at how those approaches, which we know do have a lot of benefits, how they actually restore hydrologic resilience and hydrologic processes and connectivity in our stream and stream corridor systems. Here are the study sites at Badger Creek. So this is just north of Badger Creek Ranch. This is BLM, County Road 51. We've got the control reach up here. This did not receive a treatment. This is on state land board land. And then a treatment reach just upstream of Badger Creek Ranch. This is where the kind of upper part of this and all the way down to Badger Creek Ranch was restored last year in 2021 by Ecometrics. We installed in 2021 2 groundwater transects at each site. So these pink dots are the transects that go perpendicular to the stream across the valley bottom. And they're measuring groundwater elevation over time. We have 3 surface water sensors, which are the blue triangles, and that's measuring the height of surface water coming in and out of the stream, as well as across one of these transects. And then the same setup on the treatment reach. We also have a meteorological station, which I'll talk about in a second. Storm monitoring surface water, this is what the gauges look like. It's just measuring the stage, and this spring we'll be going out and taking discharge measurements to help create a rating curve and understand the flow rate. And we're looking at how the stage in the channel is related to the groundwater elevation nearby, and also trying to estimate the inputs and outputs of the surface water and in each reach. Here's our installing of groundwater wells with Bureau of Land Management. Thanks very much to Aaron and folks that came out from BLM to help. For the groundwater, we're looking at, again, how the surface and subsurface are connected. We're also going to be estimating the contributions to discharge or to stream flow from groundwater and how that varies across the season, and then how much we're storing in the groundwater in the treated reach versus the restored reach. And there's Buffy helping develop some of our wells. The last piece of this is evapotranspiration. This is our meteorological station. We'll have, we just had rain data from last year, but now we've got all the equipment to be able to do temperature and humidity and solar radiation, so we can calculate evapotranspiration using this satellite imagery, which is NDVI, or how much photosynthetic activity is happening in the river corridor. So let's look at some data. We've got, these are the loggers, groundwater loggers that we put in. And what we see is the rainfall data over time for each day. So we got some good rain events over the summer. And then on the bottom, we see the groundwater response. And this is just one groundwater well, and this is the elevation in that well. This is at the treatment site where we see a big bump. I think it's about 1 foot of water coming up after the restoration occurred. So we're kind of filling up the groundwater table there. And then we see groundwater responses to these different flood events that come through. What I'm going to talk about is the relationship between wells that are near the channel So here's a near well and then wells that are far away, and looking at the relative elevation between those two. So near is near the channel and far is far away. And we can see that during base flow conditions, the light blue or the far is a little bit higher, a little bit elevated. That means that the groundwater is sloping towards the channel and contributing to the channel. So the channel is getting water from the nearby hill slope water table. And that means the stream is a gaining stream. It's under gaining conditions. During flood events, the water table is actually elevated near the channel relative to far away. And so the gradient changes or the slope changes, and the water table is now flowing back towards away from the channel, and the channel is contributing to the groundwater table. So we'll look at that relationship across the control and the treatment sites. For the control site, we had losing conditions, meaning the channel is recharging the water table or the alluvial aquifer near the channel in the floodplain about 2% of the time. So we had 2 flood events where that occurred, where there's enough water in the channel to kind of spill back into the floodplain, and where the near elevation was greater than the far elevation. So or water is flowing back into the floodplain. For the treatment site, it was quite a lot longer. Of course, we did have a filling period after the treatment. So when the restoration treatment went in, those sod speed bumps, we had a decent amount of time where it filled in, but we'll note that these bars are thicker compared to the control site. So we had actually a lot more filling time happening at the treatment site. More water potentially was being stored. Now we'll look at actually transects, so kind of cross sections of the water table at these sites. And we're just taking the elevation of the water table at 4 of these monitoring wells and looking at what that transect looks like, or that cross section looks like. And so I took 4 different time periods. So we just sliced these different time periods before and then during these flood events to look at how the groundwater elevation transects changed over time. And so here's for that first time period, we've got the before the flood in dark green, and then during the flood in light green. And it's pretty flat. There's not a lot of gradients, especially during the flood period, where we see just that obviously water is flowing into. You can see right here, there's a little bit of a slope from near the channel to far away of the channel. That means the water is flowing back this way. But it's not very strong. And if we have this bigger flood event, we can see it a little bit more clearly. So here's the pre-flood condition where the hill slope is contributing to the channel, or the groundwater table is contributing to this channel. And then during the flood, the channel is pouring back into the floodplain here. And you can see just a little bit more of a slope away from the channel. At the treatment sites, this is much stronger. We can see for this moderate flood events that there is a pretty significant slope right there. You can see that. And then for the flood event, this is a much greater slope. So the greater the slope, the more water is flowing away from the channel and back into the floodplain. What we're seeing here is a cartoon showing it under gaining conditions. The water table is flowing to the channel, contributing discharge to the channel. During flood conditions, the high flow is putting water back into the banks and floodplains. So now we have some more work to do. The additional questions we're pursuing is how much additional water is stored in the surface and subsurface and the treatment site per unit length. And that's going to be changing over time. How long does this water remain in storage and contributing to extended flows after flood events? And what is the magnitude of evapotranspiration for each reach and per unit length? And does it vary between the treatment and control sites? So these are some of the big questions we're still looking at. We also need to work on the surface water balance. And ultimately, we're going to have some estimates of all the different contributors to the water. So we have the groundwater table, the storage and the reach, inputs, outputs on the surface, and then evapotranspiration. Looking ahead, and over the next year or two, as this project unfolds, we're going to be calculating evapotranspiration, as I said before, using our meteorological data, the satellite imagery, and this model, it's called metric, that will help us calculate evapotranspiration. We'll be coming out in the spring. It's looking like the second to last weekend in May, and we'll be coordinating with you all about that. We're going to deploy the loggers for the groundwater and surface water, the meteorological station. We're going to do some slug testing, which allows us to estimate how fast water moves through the aquifer. And then that will allow us to estimate flow rates into and out of the aquifer. We'll look at how flow rate is changing in the channel as we move downstream across the control and treatment sites. And then we'll take those surface water discharge measurements to make our rating curve. That allows us to translate the stage or elevation of the water table or the surface water with the flow rate. And that's all I've got. Thanks so much, and look forward to continuing working with you all.